Hi friends, welcome to this class. This is third class on Suzuki reaction, right? So we were discussing about some examples of Suzuki reaction. Let us see few more examples. See here, we know that this is acid RCOOH, right? To convert this into ketone RCOR, it is very difficult, right? So what we used to do is we need to add SOCl2, thionyl chloride, and we used to get RCOCl. Right, RCOCl. To this we need to get this ketone, we need to add only one equivalent. If this is one equivalent and only one equivalent, you should add RMgX, right, Grignard reagent. If these are X's, instead of getting ketone, it will be again reduced to tertiary alcohol like this, right? So we need to add this only one equivalent, this one equivalent, this one equivalent, we get ketone. If excess of this, we get alcohol. So this is very tough, right? And also this reaction, like what is this? Amide, right? To convert amide into ketone, it is very difficult because NH2 is bad leaving group. It won't leave. If here chlorine is there, however, we can do using Grignard reagent only one equivalent. This chlorine will leave and R will add here, right? Nucleophilic carbonyl substitution reactions. These things we have studied, and also I will make videos. You will get it. No worry. So, but here NH2 is a very bad leaving group. So the getting it into ketone is very difficult. But using Suzuki reaction, we get using this amide we can form this ketone compounds also. So this is the benefit of Suzuki reaction. Because of all these benefits, he got Nobel Prize, right? So how he used to do the reaction? So what he did is he took amide. This amide he took. This amide, because of this lone pair, it used to donate like this. So this carbon nitrogen bond was very strong because of this kind of resonance. So what he did, he protected this amine in Bock protected. So what he got? RCONH Bock protection. You should know this, right? This is Bock protection. This is compound. Here nitrogen will donate its electron density, right? And it will go back and it will take, this bond will go. So the Bock is, this structure is nothing but like this only, RCONH, and Bock structure is this one, NC double bond O and tertiary group here. This is Bock. Instead of writing all this structure, we simply write as Bock. So the scientist did, he took this amide and he protected this nitrogen using Bock. Because of this, we saw that in the structure of Bock, the lone pair are resonated like this also. So this bond was, initially this bond was very strong because resonation was only like this. But here now resonance is like this way also, like this way also. Compared to this bond is weak, right? So here he added palladium catalyzed, PDL2. So what happens? The palladium inserted between this bond. So here PD and nitrogen protected with Bock, and here ligand and here ligand, right? So to remove this, let me tell you. So, and in transmetallation step, what he did is he took this thing, we want ketone, right? So what he took are boric acid, organic boron compounds, and he added this base. Instead of base, potassium fluoride he added, because K plus F minus fluoride ion. So this activates this, and this R will like this nucleophilic substitution, right? And potassium, this compound we will get, and in the transmetallation step we got this thing, palladium, and here R, and here on ligand, here ligand. Here it is again in +2 oxidation state. Initially it was 0 oxidation state and +2. In reductive elimination I have told this thing, right? So this is reductive elimination, and the product what we got is CO R, ketone, and this PdL2, zero oxidation state, reductive elimination. So here it is oxidative addition, transmetallation, reductive elimination. That is nothing but Suzuki reaction, right? So to make this bond weak, what it is, he protected his nitrogen block so that lone pair are again involved in that way, right? So in this way he made the bond weaker, and instead of using base, this is KF. So all these are nothing but modified Suzuki reactions, right? And also not only amide, he made this acid also convert into ketone using this Suzuki reaction. What he did is, this is acid, so he converted it to like BNOH. This is alcohol. BNOH, you should know the structure. C6H5CH2OH. This is nothing but BNOH. BN means benzyl. BN means this benzyl. C6H5CH2 group linked to something benzyl. BZ means benzoyl. Benzoyl. C6H5CO, and this carbon is connected to something else, right? This is benzoyl and this is benzyl, right? So what he did, he converted into esters, RCOOBN. Again here same thing, palladium he used in zero oxidation state, so it is oxidative addition, and one more reagent ketone he need add. So in transmetallation he made use of this esters or boronic esters or boric acid, and presence of base KF OH minus and activated, and followed by trans elimination. So what he used to get, he got RCOR. From acid he could able to convert into ketone. Similarly from amide he could able to convert into ketone using Suzuki reaction, right? Because of all these steps he got this Nobel Prize, because these reactions can't be done that too more efficiently. We won't get more yield. We can do those reactions in lab also, but the yield will be less as we do in a regular lab. But using this palladium catalyzed Suzuki reaction, we used to get more yield. So he made tough reactions so easy, so he got the Nobel Prize, right? So few more reactions. So this is cyclic compound, tricyclic, and ER means aryl group, and TS means it is a tosyl group, you should know, right? So here what he did, palladium. So palladium inserted here. During this insertion, what happened is that SN2 kind of here zero oxidation state, right? It inserted in such a way that SN2 reaction type kind of reaction occurs. Let me write first reagent everything. So first they used some palladium catalyst. Second step, in transmetallation they used this Na2CO3 carbonate. Instead of using NaOH or tertiary butoxide base, they used this kind of base, right? And third step, transmetallation, ER dash, let me write here, it is BOH in presence of same base Na2CO3. And fourth one, solvent they have given toluene and water system. Toluene, which is organic, plus water, which is aqueous or inorganic. Toluene and water solvent they used, and the product they got like this. Here they have written ER dash, right? So the same ER dash, NH, TS, and here AR. One thing you should remember, here the AR is above the plane, and here also AR is above the plane. So retention of stereochemistry has happened, right? And one more thing I have forgotten to tell. In reductive elimination, I told here palladium will be there, here one R, and here R dash, let us take, and ligand. Two state, right? Reductive elimination will be like these two should be cis form, and palladium form plus 2, it comes to zero oxidation state, right? And R dash bond form happened. The rate of reductive elimination will be more for this kind of reaction. For example, aromatic and aromatic. Next, aromatic and sp3 alkyl. Least is alkyl and alkyl. Why this is? Because the bond between these two will be very strong. Stronger the bond, greater will be the reductive elimination step. Like this, you remember. So reductive elimination, the order will be like this: AR, ER, ARR, and R. So these things you need to remember. So how this reaction occurs? Let us see. This one reaction and one more reaction, and then we will end up this Suzuki reaction. Right. So how this happens is, first step, palladium when we add to this, the palladium will insert in such a way that this will insert here and this bond will be broken, because three-membered ring, ring strain will be more, right? Because of that ring strain, it will be broken. How it will break? Like SL2 reaction kind of reaction occurs, and here palladium will be there, this carbon, and SN2 means above will become below AR, right? And CH2 N minus tosyl group TS. This N minus will be linking with palladium for momentary purpose, but this reaction is taking place in water medium, solvent is there, so here it will get proton. How it will get? You know that N minus, water will be there, HOH, H2O we can write as HOH. It will give its electron density and it becomes NH, right? The same reaction. So this compound we get, right? So this is nothing but oxidative addition. From zero oxidation state, it has come to +2 oxidation state. Further transmetallation step, we have used Na2CO3, right? AR dash B OH OH. Na2CO3 structure you should know. C double bond O minus, and Na plus. This is the sodium carbonate. Na2CO3 means sodium carbonate structure. So what it will do? It activates this organoboron compound. So what we get? Ar, boron, OH, and here this O, CO, O minus, Na plus. Right? So here negative charge. So followed by nucleophilic substitution reaction. That is nothing but, what is that? Transmetallation step, right? Transmetallation. So we get palladium NHTS, and here AR, and this is below the plane AR, and here I have written as AR dash, right? So this is nothing but AR dash. So reductive elimination, it is also like SN2. So again inversion of configuration. Initially it was above, it became below, and again SN2. So from below it will become above, like this. So it will be AR dash AR NHTS. So here from here, see, it was above, we got the product above, right? Retention of configuration, that is nothing but Suzuki reaction. So this one is also one of the example of Suzuki reaction. Let us see one more last example of Suzuki reaction. It is also very easy. See here, R, halogen, any kind of halogen. Here also any kind of halogen. Chlorine, bromine, same kind of halogen. So they observe that scientists, in presence of palladium catalyzed, those the transmetallation step, everything, they observe that. Let me take here like compound like R dash CH2 BOH, transmetallation in presence of base, any kind, Na2CO3, sodium carbonate, or NaOH, or potassium tertiary butoxide. We can use any kind of base, and they saw that only this kind of product they saw. What kind of product? 1 2 R 1 2, sorry, correct na? 1 2 second R and halogen, right? Only this product they observed, not this kind of product. R double bond here, 1 2 R. This product they didn't observe. Why? Because they saw that only the trans to this double bond. See here, this is double bond, this is trans, right? And this one is cis. Only trans halogen left the group giving this product, not the cis. This product we didn't get. This is cis product, right? This is cis product, whereas this one is trans product. In Suzuki reaction we observed only trans product, because in regard to elimination step, whenever there is migration of substituent, the configurations will retain, that we discussed in last example. Stereochemistry will be retained, and also the Suzuki reaction favors trans addition compared to cis kind of addition. These things you need to remember. In next class we shall see few more named reaction. Till then, take care.